I've modified an AP Chemistry FRQ question on acids and bases. This FRQ accounted for 11% of the exam points on a published exam. The acid-base questions typically account for at least 15% of the questions on a AP Chemistry exam. My 10-point FRQ covers almost all the skills and knowledge required for the AP Chemistry exam's acid-base section. It covers pH, pOH, strong and weak acids, equilibria, acid-base reactions, titrations, buffers, and my favorite, the Henderson-Hasselbalch equation. To get the complete FRQ, go to my AP Chemistry site, chemadvantage.net, and scroll down to Course Documents. Then download and print the FRQ. Get your calculator and an AP equation sheet and do your best to answer the questions in the 24-minute time limit. Then you can use my 5 videos to grade your FRQ and also learn what you need for the AP Chem exam. Here's my explanation for Part A. This is a FRQ question that was used pretty recently, and it's such a good one. I think I'd like to try and explain it step by step. So I'm going to do A first. Here it is. The acid, typically in FRQ, they'll come up with something that you never heard of, like sorbic acid. Well, maybe you've heard of sorbic acid, but you've never seen it before. But, don't worry about that. It's just sorbic, and it's an acid. So it's got its little H here, and then, C6H7O2. Probably an interesting molecular structure, but basically we're just thinking HA, sour flavoring, so forth. Yeah. Now here's the critical part. The concentration of this weak acid must be determined. So that's the bottom line in this question. We're going to find its concentration. How concentrated is this sorbic acid? Now, it's done with a titration where a student titrates 45 mLs of solution. So this is 45 mLs of our acid. So our HA, we'll color code the acid as green. HA, our HA volume is 45 mLs. Okay, we may have to refer back to that later. Now we're titrating it with a base. That's what it looks like here. And I'm going to switch over to red on my highlighter for the base. So we've got some sodium hydroxide. Sodium hydroxide is a strong base. Now we can forget about the sodium pretty much. It's the hydroxide we worry about. It's a 1/4 molar using both an indicator and pH meter. Now they're giving us the Ka for sorbic acid. It's a moderately weak acid. It's a lot like acetic acid, in fact, which is 1.8 times 10 to the -5. Okay, we've got a weak acid and strong base. So we're going to be starting at a pH of 3, adding some base to it. It's going to get half titration, then half equivalence. Then we're going to have the equivalence, which is going to be slightly basic. Let's see what they ask first. Which of the following are molecular and net ionic equations for this reaction? First, let's do the molecular. Let's try our molecular first. I'll get my little pen. Molecular starts with a molecule. So here's our first molecule. And here we go. There's our molecular acid. It's a weak acid. And it's going to be primarily in this form. It's going to, very, very little of it changes into H+, and it's sorbate. So we've got our molecules of weak acid, our HA. We're going to react it with our base, sodium hydroxide. Now, as I said, that Na is irrelevant, but they asked for the molecular equation, and it is sodium hydroxide. So if it were a molecule or an ionic substance, it would be NaOH. And as an acid-base reaction, the H is going to end up coming over here, and the Na is going to come over there. We get the sodium sorbate and the HOH, the water. That's our molecular equation. Now the tricky part, and this is what they usually ask for, is the net ionic equation. Now, as I said, this is a weak acid. As a weak acid, it stays together mostly as C6H7O2, H sorbate. The shape, and I'll reveal the first part of our net ionic equation. Because it's a weak acid, we don't write it as being ionized, because it usually isn't. 99.5% of it might just be in this form, and very, very little turns into H+. However, that's not the case with sodium hydroxide. Sodium is soluble. We know all sodium compounds, potassium compounds, ammonium compounds break up into ions, and they become these spectator ions. So I'll get my pen out, and I'll say, forget about the sodium. Forget about it. It's not going to be there. Not in any net ionic reaction. Sodium's never going to make a precipitate. And so instead of saying sodium hydroxide or net ionic equation, we say hydroxide ions. And those hydroxide ions are going to undergo our little acid-base reaction. They're going to 100% react with the acid. I mean, that's the nice thing about hydroxide. I don't care, if you've got a weak acid by it, it's going to zap and accept that proton from the sorbate. So our sorbate is just going to be hanging out there as an ion. It'll be sodium sorbate. It'll have the sodium ions matching it, but it's going to be floating around. It'll provide that little sour taste that you get in a lot of drinks added to make the stuff taste sour. And water. Acid's going to be wiped out by the base and turned into sorbate and H2O. Now later on, the sorbate's going to get its revenge by being a weak base and make our solution slightly basic, but once all the acid's gone. But that's it. That's it. Be able to write a net ionic equation. This is it. This is probably what's going to be asked on an AP question. Okay, I just answered A. I'm going to go on and answer B in the next video. So we got this first part. This is worth, nice solid point. Don't lose the net ionic equation points because you've forgotten that weak acids are molecules.